On the night of June 17th, 2026, a magnitude 6.6 earthquake tore open the floor of the Atlantic Ocean, and for a few minutes the machines that watch for the end of the world thought a wave might already be coming. An automated alert fired, carrying the two words that move people faster than almost any others: tsunami, threat. And then, just as fast, it was taken back. No warning, no danger to anyone. But here is what should keep you watching tonight, because the reason that wave never came is the exact same reason that tells us what it would take for the next one to be real. The ocean we call the safe one is hiding something along its entire spine. Before we go any further, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs, and drop a comment telling me where you're watching from tonight. Let's get into it. Part 1. The alert that came from nowhere. Somewhere in the middle of the Atlantic Ocean, on the night of June 17th, 2026, the floor of the sea tore itself open, and for a few minutes the machines that watch for the end of the world thought a wave might already be coming. A magnitude 6.6 earthquake had just ruptured the seabed at a place so far from any shoreline that if you stood on a boat directly above it, you would see nothing in any direction but water to the horizon. An automated message went out, the kind that is built to fire the instant a large quake strikes under the ocean, and it carried the two words that move people faster than almost any others in the English language: tsunami, threat. And then, almost as quickly as it appeared, the threat was taken back. No warning was issued, no coastline was told to run. The agencies that monitor the seas looked at what had happened, and they said the thing that should be reassuring and is somehow stranger than the fear itself. There is no danger. None. Not to Brazil, not to West Africa, not to the Caribbean, not to anyone. You would think that would be the end of it. A quake in the middle of nowhere, no wave, no victims, a non-event. But I want you to sit with the question that the machines asked and then answered in the space of a few minutes, because the answer is far more unsettling than the question. Why did the ocean not rise? A magnitude 6.6 is not small. It released roughly the energy of a large nuclear weapon into the shallow crust beneath the sea. The seabed genuinely ruptured, and yet the water above it barely noticed. That is not luck. That is physics, and once you understand the physics, you understand something about the planet that very few people ever think about, and that almost nobody finds comforting once they truly grasp it. Here is the thread I'm going to pull on for the next couple of hours, and I need you to hold on to it, because everything else connects back to it. The reason this earthquake made no wave is the same reason that tells us exactly what it would take for the next one to make a wave that does not stop until it reaches a beach. The ocean we think of as the safe one, the quiet one, the one with no ring of fire and no great subduction zones lining its shores, is alive along its entire spine, and the line between no threat and evacuate the coast is thinner and rests on a stranger set of conditions than you have ever been told. I want to dwell for a moment on that word tsunami, because of what it does to the human nervous system. We carry the memory of 2004 and of 2011, when the ocean rose without mercy and took hundreds of thousands of lives between them, and ever since the word has functioned almost like a fire alarm wired directly into the oldest part of the brain. The instant it appears, we picture the sea pulling back from the sand, the strange exposed seabed, the dark line on the horizon that grows instead of fades. That reflex exists for a good reason. It has saved lives where people learned to run the moment the water retreated. But a reflex is not an analysis, and the gap between the two is exactly where this story lives. The machine that fired the alert on June 17th was, in a sense, running on that same reflex, automated, instant, cautious by design. And the humans and the physics that overruled it were doing the slower, harder thing, asking not is this an earthquake under the ocean, but is this the specific kind of earthquake that can lift the ocean? It helps to understand what that alert system actually is. Around the world, a small number of tsunami warning centers watch the planet's seismographs around the clock, and they are built around a brutal constraint, which is time. A tsunami can cross an open ocean at the speed of a jetliner, so when a large undersea earthquake is detected, the centers have only minutes to decide whether to alert coastlines that might lie in the path of a wave. They cannot wait for certainty, so the first response is almost reflexive, triggered by a few basic facts: the magnitude, the depth, the fact that it happened underwater. A message goes out flagging the possibility, and then, in the minutes that follow, the analysts refine the picture, looking at the type of faulting, the exact location, the readings from any nearby sea level gauges, and they either escalate the alert into a genuine warning or they stand it down. On June 17th, the standing down happened fast, and it happened with confidence, and that confidence is the thing worth understanding. Consider, too, just how much raw power we're talking about, because it makes the calm of the sea even more remarkable. A magnitude 6.6 earthquake releases energy on the order of a large nuclear detonation, tens of times more than the bomb that leveled Hiroshima, all of it delivered into the shallow crust beneath the seabed in a matter of seconds. The ground genuinely lurched. Seismometers on the far side of the planet registered the passage of the waves. If that same amount of energy had been delivered in the right way, in the right place, it would have been more than enough to threaten a coastline, and yet the surface of the ocean directly above it rose and fell by almost nothing. That is the paradox that should be nagging at you, and it is the paradox the rest of this video exists to resolve: an immense release of energy and a sea that barely flinched. I think there is a reason the phrase "no threat" feels so strangely unsatisfying when it comes to the ocean, and it is worth naming. We are land animals, and the sea has always been the place at the edge of our understanding, the surface we cannot see beneath, the source of storms and monsters in every old story we ever told. When something violent happens out there, in the dark water, our instinct is not relief at being told it is fine. Our instinct is suspicion that we are missing something. And in this one case, that instinct is not entirely wrong, not because there was a hidden danger on June 17th, but because the reassurance came with an asterisk that no one bothered to read aloud. The ocean was safe that night for specific reasons, and the same reasons, examined honestly, tell you exactly when it would not be safe. The all clear was true, it was just not the whole story, and the whole story is what we are here for, so I am not going to leave you with the simple version, the version where a quake happened in the middle of nowhere, and nothing came of it, and we all move on. I am going to give you the version where you understand the machine well enough to read it yourself, so that the next time those two words flash across a screen, tsunami and threat, you will know which questions to ask, and you will know that the answer depends on three things, and only three things, and that the ocean's mood on any given night comes down to how those three things happen to fall. To understand why an alert fired in the middle of the Atlantic, you first have to understand that there is a wound running down the middle of that ocean, from the top of the world nearly to the bottom, and it has been bleeding new rock for longer than there have been human beings to notice. The earthquake happened on that wound, and the wound has a name. Before we get to why the water stayed flat, I have to take you to the exact spot where the ground broke, because it is one of the loneliest places that exists on the surface of this planet, and what is happening there right now never truly stops. Part 2. The loneliest place. A quake can happen. The earthquake struck at a point in the equatorial Atlantic, almost exactly on the equator, near 0.4 degrees south and 20 degrees west. I want to put that location in perspective, because the numbers do not mean much until you picture them. Draw a line from the easternmost bulge of Brazil straight across the ocean to the coast of West Africa, somewhere around Sierra Leone and Liberia. The quake happened out in the middle of that line, more than 1,000 miles from land in either direction. There are no cities there. There are no islands to speak of. There is no one. It is, by almost any measure, one of the most remote pieces of the planet that a large earthquake can possibly choose, and on the night of June 17th, that is exactly where the planet chose to release its energy. The main shock came in at 1856 Coordinated Universal Time, magnitude 6.6, logged by the United States Geological Survey and confirmed by the European seismic agencies at a shallow depth of about 10 kilometers below the seabed. Shallow matters, and we will come back to why, because shallow earthquakes are the ones that move the surface the most violently, and shallow earthquakes under the ocean are the ones capable of moving water. But here is the first piece of the strangeness. It did not come alone. The big one was the opening act, not the whole show. Over the next roughly 24 hours, that same lonely stretch of seabed kept moving. A magnitude 5.5 struck in the early hours of June 18th. A magnitude 5.4 followed. A magnitude 5.1 hit at around 2:44 in the morning, universal time, just a short distance from the others. These were not scattered around the globe. They were stacked almost on top of one another, all within a few tens of kilometers, all on the same line, all part of a single coordinated convulsion of the seafloor. Scientists call a cluster like this a swarm, a burst of strong quakes of similar size rather than one dominant shock followed by a gentle tail of fading aftershocks. And a swarm of magnitude 5 and 6 events on this particular feature is, for reasons I will explain, genuinely on the larger and more energetic end of what this place normally produces. If you have been watching the channel over the last couple of nights, your mind is probably already jumping to the other side of the world, and you are right to make the connection, because we have been tracking a very loud sequence in the Pacific. Hold that thought. The temptation to link the two is enormous, and I promise we will deal with it honestly later, because the question of whether one side of the planet can set off the other is one of the most fascinating and most abused ideas in all of Earth science. But for now, keep your eyes on the Atlantic, because this swarm happened on a structure that most people have never heard of, and that is, without exaggeration, the single largest geological feature on the face of the Earth. I want you to really feel how remote this place is, because remoteness turns out to be one of the 3 things that kept the world safe that night. The spot near 0.4 degrees south and 20 degrees west sits in the open equatorial Atlantic, in the band of ocean that old sailors called the doldrums, a region of light and fickle winds far from any shipping lane that matters. The water beneath the surface there is more than 3 kilometers down to the abyssal plain on either side of the ridge. There is no island for 1,000 miles in most directions. There is no oil platform, no fishing fleet to speak of, no instrument bobbing on the surface to feel the seabed move. If a wave had been born there, it would have raced outward across the most enormous expanse of empty water on the planet, with nothing to strike for hour after hour. The emptiness is so complete that, in a very real sense, the most dangerous thing the earthquake did was frighten a computer, and yet that emptiness hides a world that is anything but lifeless. Along the ridge, where the heat of the planet leaks up through the young seafloor, there are hydrothermal vents, chimneys of mineral-rich water superheated by the rock below, and around them cluster some of the strangest communities of life on Earth, creatures that live not on sunlight but on chemistry, in permanent darkness, kilometers beneath the waves. The ridge is not a barren scar. It is one of the most biologically extraordinary frontiers we have, a place where life figured out how to make a living from the raw energy of the planet itself. So when the seabed convulsed on June 17th, it convulsed in a place that is empty of people, but full of a kind of life we're only beginning to understand, on the most productive geological feature on the planet. The loneliness is only a human measurement, and yet we knew about it almost instantly, which is its own small marvel worth pausing on. How do we detect a magnitude 6.6 in a place where no human being was within 1,000 miles? The answer is that the planet is now wrapped in a web of listening. Seismometers on every continent feel the waves of a large earthquake within minutes, and by comparing the arrival times at stations around the world, analysts can pin down the location of a quake in the middle of the ocean to within a few kilometers without anyone ever going there. There is even a global network of underwater microphones, hydrophones strung through the oceans, originally built to listen for nuclear tests, that can hear the sound of the seafloor rupturing and pick out exactly where along the ridge it happened. So a swarm of quakes in the loneliest water on Earth becomes, within minutes, a set of precise dots on a map in an operations centre thousands of miles away. We are listening to the whole planet, all the time, and on June 17th the planet had something to say. Let me also be precise about the timeline, because the shape of this sequence matters to the story. The magnitude 6.6 struck first, in the evening, universal time, on June 17th. Then, through the night and into the following morning, the cluster of strong companions arrived. The 5.5, the 5.4, the 5.1 spread across roughly the next 10 to 12 hours, all of them packed into the same small patch of ridge. That is not the signature of a single rock snapping once and then going quiet. It is the signature of a fault system unzipping in stages, one section failing and shifting the load onto the next, which fails in turn. Seismologists watch the size and timing of these companions closely, because the pattern tells them whether a sequence is winding down or whether the largest event might still be ahead. In this case, the behaviour was consistent with a swarm releasing accumulated strain rather than building towards something bigger, which is part of why the experts remained calm even as the ground kept moving. So keep the thread in view, because every detail here serves it. The earthquake happened in the emptiest water on Earth, on the planet's longest mountain range, as a swarm rather than a single shock, and we knew all of this within minutes because we are listening everywhere at once. None of those facts by themselves tell us whether a wave was coming. For that, we needed to know what kind of fault had moved, and in which direction. And the structure that determined the answer is the most enormous and least known feature on the face of the Earth. The automated systems did exactly what they were designed to do. A large, shallow, undersea earthquake tripped the alert. A tsunami evaluation message was generated, reference to that lonely point near 0.4 degrees south, and then the human analysts and the physics caught up with the machine, and the evaluation was stood down to no threat at all. The question is why? To answer it, I have to show you the wound itself, and I have to show you that it is not a wound at all. It is the most productive factory on the planet, and it has been running for almost 200 million years. Part 3. The longest mountain range you will never see. There is a mountain range on this planet that is longer than the Andes, the Rockies, and the Himalayas combined, and almost no human eye has ever looked at it directly. It runs for more than 16,000 kilometers, it wraps around the globe like the seam on a baseball, and it is hidden under an average of about 2.5 kilometers of seawater. We call the Atlantic stretch of it the Mid-Atlantic Ridge, and it runs straight down the middle of the ocean from the edge of the Arctic, past Iceland, which is one of the only places it pokes above the waves, all the way down toward the latitude of Antarctica. The earthquake on June 17th happened on this ridge, and to understand the ridge is to understand why the ground there breaks the way it does. The Mid-Atlantic Ridge is not a scar from something that happened in the past. It is happening right now, tonight, as you listen to this. It is a divergent boundary, which is the technical way of saying it is the place where two of the great plates of the Earth's crust are pulling away from each other. On one side, the plate carrying South America drifts slowly west. On the other, the plate carrying Africa drifts slowly east. And in the gap between them, molten rock from the mantle rises up, cools and freezes into brand new ocean floor. The Atlantic Ocean is not a fixed thing. It is getting wider every single year, and the ridge is the assembly line where the new ocean is manufactured. How fast? Slower than you would guess and faster than you would believe, depending on how you think about it. The central Atlantic spreads at roughly 25 millimeters a year. That is about the speed your fingernails grow. It sounds trivial, almost laughable, until you remember that it has been doing this without stopping for nearly 200 million years. 25 millimeters a year, multiplied by that kind of time, is how you build an ocean from a crack. Every inch of the floor of the Atlantic, the entire basin, all of that water resting on rock that was once squeezed out of this ridge like toothpaste from a tube, frozen in place, and carried slowly outward to make room for more. The ground that broke on June 17th was fresh rock, geologically speaking, sitting right at the seam where the newest crust on the planet is born. This is the central fact I need you to carry forward, because it is the key to the entire mystery of the missing wave. The Mid-Atlantic Ridge is a place where the crust is being pulled apart, and that single property, the pulling apart, shapes everything about how its earthquakes behave, including whether or not they can raise the sea. The Pacific Ocean is ringed by subduction zones, places where plates collide and one dives beneath the other, and those are the great tsunami factories of the world. The Atlantic has almost nothing like that. Its defining feature is not collision but separation, and separation, as we are about to see, moves the ground in a direction that the ocean above it can mostly ignore. It is worth remembering how recently we learned that this ridge even exists in the form we now understand. For most of human history, the bottom of the ocean was imagined as a featureless plain, a flat and lifeless floor. The first hints came in the 1850s, when crews laying the first telegraph cables across the Atlantic found a broad rise in the middle of the ocean. But the real picture did not emerge until the middle of the 20th century, when a geologist named Bruce Heason and a cartographer named Marie Tharp began turning thousands of sonar depth readings into the first detailed maps of the Atlantic floor. Tharp noticed something that, at the time, sounded almost heretical. Running down the very crest of the ridge was a continuous valley, a rift, as though the seafloor were being split apart from within. She was, at first, told this looked too much like the forbidden idea that continents move. She was right, and the doubters were wrong. What Tharp had found was the surface expression of the engine that drives the entire planet. In the decades that followed, that rift valley became one of the central pieces of evidence for the theory of plate tectonics, the revolutionary idea that the Earth's outer shell is broken into rigid plates that move, collide, and pull apart. The proof came from the rock itself. As molten material rises at the ridge and freezes, it locks in a record of the Earth's magnetic field, and because that field flips its polarity every so often over geologic time, the new seafloor spreading out from the ridge carries a pattern of magnetic stripes, like a barcode, symmetrical on both sides of the crest. Read that barcode outward from the ridge, and you are reading the age of the ocean floor, growing steadily older the farther you get from the seam. It was the smoking gun. The Atlantic really is being manufactured at its middle and carried outward in both directions, exactly as Tharp's Rift Valley suggested. I find it genuinely remarkable that all of this, the realization that the longest mountain range on the planet runs down the bottom of the sea, that it is the birthplace of new crust, that it is the reason the continents drift, was worked out within the lifetimes of people still alive today. We have, to this day, mapped the surfaces of Mars and Venus in finer detail than most of the floor of our own ocean, and only a tiny fraction of the seabed has ever been seen directly by human eyes or cameras. The Mid-Atlantic Ridge is the largest single feature on the planet, and yet it remains one of the least visited places in the solar system that we can technically reach. Most of what we know about it comes from sonar, from the magnetic barcode, and from the earthquakes themselves, which act like a slow, irregular sonar of their own, lighting up the structure of the ridge each time the ground gives way. June 17th was one of those flashes of illumination, a moment when the machinery announced itself loudly enough for the whole listening planet to take note. There is one place where you do not need a submarine to visit the ridge, and it is worth knowing about because it makes the abstraction real. The island of Iceland sits directly astride the Mid-Atlantic Ridge, which is the secret behind its volcanoes, its geysers, and its constant low rumble of earthquakes. Iceland is, in effect, a stretch of the ridge that has piled up enough volcanic rock to stand above the sea, and you can walk through a valley there where the North American and Eurasian sides are visibly pulling apart. A crack in the earth you can stand inside. Everything that happens quietly and invisibly beneath 3 kilometers of water in the equatorial Atlantic happens in the open air in Iceland. When you picture the seam that broke on June 17th, picture that Icelandic Rift Valley, and then sink it kilometers beneath the waves and run it for thousands of miles in either direction. That is the structure the earthquake belonged to, and the earthquake on June 17th happened on the freshest, youngest rock of that floor, right at the crest of the rift, where the barcode of magnetic stripes has not yet been written, where the crust is still being born. When I say this quake happened on the seam, I mean it happened at the exact line where the planet is, at this very moment making more of itself. So we have our scene, the loneliest water on Earth, sitting above the longest mountain range on Earth, at the seam where the planet manufactures new crust, shaken by a swarm of strong earthquakes that tripped a tsunami alert and then stood it down. To understand why the water stayed flat, we now have to answer a more basic question, one that almost everyone gets wrong. What actually makes a tsunami in the first place? Because it is not the shaking. It was never the shaking. And the truth about how these waves are really born is where this story starts to turn. Part 4. What actually makes a tsunami? Almost everyone believes that earthquakes make tsunamis by shaking the water, and almost everyone is wrong. The shaking has nothing to do with it. You could shake the ocean sideways all day long and produce nothing but ripples, because water simply slides out of the way of horizontal motion. What makes a tsunami is something much more specific, and once you understand it, the missing wave in the Atlantic stops being a mystery and starts being a near certainty. A tsunami is made when a large area of the seafloor moves suddenly up or down, lifting or dropping the entire column of water sitting on top of it. It is displacement, vertical displacement, that does the work. The seabed acts like a giant paddle pushing straight up against the underside of the ocean, and the ocean has nowhere to go but outward and upward, and that bulge of displaced water spreads across the sea as a wave that can cross an entire basin. Think about it this way. If you sit in a bathtub and slide your hand back and forth through the water, the surface barely changes. But if you push a dinner plate flat against the bottom of the tub and shove it straight up toward the surface, you displace a slab of water all at once, and a surge rolls outward and slops over the edge. That is the difference, and it is the whole difference. Tsunamis are not about how hard the ground shakes. They are about whether the ground lifts. A megathrust earthquake in a subduction zone, like the ones that ring the Pacific, can heave a section of seafloor hundreds of kilometers long upward by several meters in a matter of seconds. That is the dinner plate, scaled up to the size of a country, and that is why the great killer tsunamis almost all come from those collision zones. So now hold that against what we know about the Mid-Atlantic Ridge. The ridge is not a collision zone, it is the opposite. It is a place where the crust is being pulled apart, and the earthquakes that happen along most of its length are not the kind that heave the seafloor upward. They are a different beast entirely, a beast that moves the ground in a direction the ocean can almost completely ignore. This is the hinge of our whole story. The earthquake on June 17th released the energy of a large bomb, but it released it as the wrong kind of motion. It moved the ground sideways, not up, and the ocean, faced with a sideways shove, did what water always does. It shrugged. There is more to why a tsunami is so different from an ordinary wave, and it is worth understanding, because it explains why these waves are so deceptively dangerous, and why displacement is the only thing that births them. The waves you see at the beach, the ones driven by wind, are a surface phenomenon. The wind pushes on the top of the water, and the motion only reaches down a relatively short distance below the surface. A tsunami is nothing like that. When the seafloor displaces a column of water, it sets the entire column moving, from the seabed all the way to the surface, kilometers of water from top to bottom. That is why a tsunami carries so much energy, and why it behaves so strangely. Out in the open ocean, that energy is spread through such an enormous volume of water that the wave at the surface may be only a foot or two high, so gentle that a ship passing over it would never notice. But the wave is moving at the speed of a jet aircraft, 500 miles an hour or more, and it stretches for tens or even hundreds of miles from one crest to the next. The horror comes at the coast. As that fast, low, immensely long wave races into shallow water, it is forced to slow down, and as the front of it slows, the water behind piles up into the back of it. The energy that was spread through a column kilometers tall gets compressed into a column only meters tall, and it has nowhere to go but up. The wave rears up out of the sea, and that gentle 2-foot swell in the open ocean becomes a wall of water, 10, 20, 30 feet high or more, surging inland not as a breaking wave, but as a fast, relentless flood that does not stop. This is what happened in 2004 around the Indian Ocean, and in 2011 along the coast of Japan, when megathrust earthquakes heaved the seafloor upward and sent walls of water into densely populated coasts. Hundreds of thousands of people died, and in both cases the killer was vertical displacement of the seabed, the giant paddle on a colossal scale. There is a cruel subtlety to these waves that makes them even more dangerous than their raw height suggests, and it is worth knowing because it is the difference between life and death on a real coastline. Because a tsunami is the whole water column in motion, rather than a surface wave, the first sign of it is often not a wall of water at all. It is the sea retreating, draining away from the shore, pulling back to expose a seabed that no one has ever seen bare, as the trough of that immensely long wave arrives ahead of its crest. People who do not understand what they are seeing walk out onto the exposed flats to look at the stranded fish and the suddenly visible wrecks, and then the crest arrives and there is no outrunning it. The very length of a tsunami, the fact that crest and trough can be tens of minutes apart, is what makes it a flood rather than a wave, a sea level that rises and keeps coming inland long after an ordinary wave would have spent itself. That is what makes vertical displacement so uniquely lethal, and it is exactly what the sideways grinding of June 17th could never have set in motion. There is also the matter of distance, and it cuts in a direction worth understanding. The coasts that suffer the most are usually the ones closest to the source, where the wave arrives within minutes, before any warning can possibly reach people. A tsunami born at a subduction zone right offshore gives the nearest coast almost no time at all. But the same wave, crossing an entire ocean, weakens steadily as it spreads, which is why distant shores often receive only a manageable surge. This is the location lever again, and it ran entirely in our favour on June 17th, because there was no nearby coast for a wave to ambush, and any energy at all would have had thousands of miles to fade. Now hold every bit of that against June 17th, because the contrast is the whole point. To make a tsunami, you must move the entire water column, and to move the entire water column, you must shove the seafloor up or down. The ridge earthquake released the energy of a large bomb, but it released it as a sideways grinding, and sideways grinding does not shove the water column anywhere. It is like the difference between sliding a book across a table, which barely disturbs the air above it, and slamming the same book flat onto the table, which sends a puff of air outward in all directions. Same object, same energy, completely different effect on the fluid above. The Atlantic stayed flat because the seabed slid rather than slammed, and the reason it slid rather than slammed is written into the very structure of the ridge, the structure we're about to meet. But why would a magnitude 6.6 move sideways instead of up? Why does the longest mountain range on the planet break in a way that cannot lift the sea, when the collision zones of the Pacific break in a way that can drown a coastline? The answer lives in a feature of the ridge that is so enormous, and so violent and so strange, that when scientists first mapped it, they could barely believe what they were looking at. The ridge does not just spread, it is sliced, over and over, by some of the largest faults on the entire planet, and one of them sits almost exactly where this earthquake struck. Part 5. The Faults that Grind Sideways. The mid-Atlantic ridge does not run in a single smooth line down the middle of the ocean. If you could pull the water away and look at it from above, you would see that the ridge is broken into segments, and those segments are offset from each other, shifted left and right like the rungs of a ladder that has been knocked sideways. The places where the ridge jumps from one segment to the next are called transform faults, or fracture zones, and they are where two pieces of seafloor slide horizontally past one another. This is the same kind of motion you find on the San Andreas Fault in California, where two plates grind side by side rather than one riding over the other. And here is the part that matters for our story. The equatorial Atlantic, the exact region where this earthquake struck, is home to some of the largest transform faults that exist anywhere on Earth. Just south of the equator runs a monster called the Chain Fracture Zone, and just north of it runs an even larger one, the Romanche Fracture Zone. The Romanche is almost difficult to comprehend. It offsets the ridge by roughly 900 kilometers, and along its length the seafloor plunges to nearly 7,800 meters below the surface, a gash in the ocean floor nearly as far down as some of the trenches of the Pacific. These are not minor cracks. They are among the great structural features of the planet, and the earthquakes that happen on them are overwhelmingly the side-by-side, grinding kind, the strike-slip kind, the kind that moves the ground horizontally. The swarm of June 17th and 18th happened right in this neighborhood of giant sliding faults, and that single fact predicts almost everything about why the sea stayed calm. When a strike-slip fault ruptures, the two walls of rock shift past each other horizontally. The seafloor on one side lurches in one direction, the floor on the other side lurches the opposite way, and crucially, the surface does not rise or fall very much. There is very little of that vertical paddle motion that a tsunami requires. You can release an enormous amount of energy this way, enough to shake the seabed violently, enough to be felt on instruments around the world, and still lift almost no water at all. This is why a magnitude 6.6 on a ridge transform fault is, in tsunami terms, almost harmless, while a magnitude 6.6 on a subduction megathrust could be a genuine threat to a nearby coast. The magnitude tells you how much energy was released. It does not tell you which direction the ground moved, and for tsunamis, direction is everything. Let me make the geometry of these faults clearer, because it is genuinely beautiful once you see it, and it explains why the equatorial Atlantic in particular is built for sideways motion. Picture the ridge as a long crack down the middle of the ocean, but the crack is not perfectly straight. It is broken into segments, and each segment is shifted sideways relative to its neighbor. To connect two offset segments, the seafloor has to slide horizontally along the gap between them, and that connecting gap is the transform fault. On one side of it, seafloor is moving one way as it spreads from its segment. On the other side, seafloor is moving the opposite way as it spreads from the neighboring segment. Between them, the two slabs grind past each other in opposite directions. That grinding is pure horizontal motion, and it is the defining earthquake of a transform fault. The equatorial Atlantic happens to be sliced by the largest of these offsets, anywhere on the mid-Atlantic ridge. The ridge is shoved hundreds of kilometers out of line here, and to bridge those offsets, nature built transform faults of staggering size. The Romanche, the Chain, the St. Paul systems, these are some of the longest strike-slip faults on the planet, and the Romanche in particular, with its roughly 900 kilometers of offset and its floor plunging towards 7,800 meters, is in a class with the great fracture systems of the Earth. When the ground broke near 0.4 degrees south and 20 degrees west, it broke in this neighborhood of giant sliding faults, in the part of the entire ridge most thoroughly dominated by horizontal motion. The location practically guaranteed the mechanism. There is a subtle distinction worth making here. because it shows how precisely geologists understand these features. The long scars these transforms leave in the seafloor are called fracture zones, but only part of each scar is actually active at any given time. The active stretch, the part where two pieces of seafloor are currently grinding past each other in opposite directions, lies between the two offset segments of the ridge, and that is the true transform fault, the part that makes earthquakes. Beyond it, the scar continues across the seabed as a long healed wrinkle, a fossil record of past motion, no longer seismically alive. The earthquakes of June 17th fell on the active stretch, on the living part of one of these systems, where the grinding is happening now. It is a reminder that even the apparent chaos of the seafloor is, on close inspection, organized and legible, and that a swarm of quakes here is the predictable behavior of a well-understood structure, not a mystery and not an omen. These equatorial transforms are so large that they do something almost nowhere else on the ridge does. They expose the planet's interior. Where the Romanche grinds and tears, the faulting has dragged up slabs of rock from far below the normal ocean crust. Pieces of the Earth's mantle hauled to within reach of research submersibles and dredges, which is part of why this stretch of seabed has fascinated geologists for decades. The fracture zones here are not just faults, they are windows, gashes far enough down and old enough that the layers beneath the seafloor are laid bare along their walls. So when the ground broke on June 17th, it broke in a place that is structurally extreme, even by the standards of the mid-ocean ridge, a place defined by the largest sideways offsets and the deepest gashes anywhere along the Atlantic seam. Everything about the setting funneled the energy into horizontal motion. It is the same family of motion as California's San Andreas Fault, and that comparison is useful for a reason that might surprise you. The San Andreas is capable of producing a magnitude 7 or even nearly 8 earthquake, a genuine catastrophe for the cities along it. But notice something. We do not warn the California coast about tsunamis from the San Andreas, because the fault moves sideways, and sideways motion on land or under the sea does not lift water. Strike-slip earthquakes, as a category, are simply poor tsunami generators, even at large magnitudes, even when they happen offshore. There are rare exceptions, usually when a strike-slip quake also triggers an underwater landslide, and we will get to landslides because they matter enormously. But the basic rule holds. A grinding sideways fault releases its violence into shaking, not into lifting, and the equatorial mid-Atlantic ridge is one of the most grinding sideways places in the entire ocean. So when you put the pieces together, the missing wave stops being a mystery at all. The largest transform faults on the ridge sit in the equatorial Atlantic. Transform faults move horizontally. Horizontal motion does not displace the water column. Therefore, an earthquake here, even a strong one, even a swarm of them, releases its energy almost entirely as shaking that the open ocean above can absorb without rising. Every link in that chain is solid, and every link points the same direction, toward a calm sea. Let me bring this all the way back to the thread that ties this whole story together. The earthquake made no wave because it happened on a sliding fault, in a place defined by sliding faults, where the dominant motion of the ground is horizontal. NOAA did not get lucky when it declared no threat. The geology of the equatorial mid-Atlantic ridge made the answer almost a foregone conclusion before any analyst even looked at the data. But notice what we have quietly established here. The reason there was no tsunami is specific. It depends on the type of fault, the direction of motion, the local structure of the seabed, which means that if you change those specifics, you change the answer. And that is the door through which the real fear in this story walks in. Hold that, because before we open that door, I have to explain one more thing about this ridge that makes it even less likely to threaten anyone, and it is the very thing that also makes this particular swarm so unusual. Part 6. Why the verdict was no threat. When the agencies that watch the world's oceans declared that the June 17th earthquake posed no tsunami threat to any region, they were not making a hopeful guess. They were reading a verdict that the planet had already written into the rock. And I want to walk through that verdict carefully, because understanding why they could be so confident so fast is the thing that separates real understanding from the kind of fear that the words tsunami threat trigger in all of us automatically. The confidence came from 3 facts lining up, and all 3 point the same way. The first fact is the mechanism, which we have already covered. A strike-slip rupture on a ridge transform fault moves the ground sideways, and sideways motion does not lift the sea. The second fact is the location. This earthquake happened more than 1,000 miles from the nearest significant coastline, in the middle of an ocean that has no subduction zones lining its shores to amplify or focus a wave. Even in the unlikely event that some small amount of water had been displaced, it would have spread outward across thousands of miles of open ocean, losing height the entire way, arriving at any distant shore as something barely distinguishable from a normal tide. And the third fact is the historical record. Earthquakes happen on this part of the mid-Atlantic ridge regularly, year after year, and they have a long, consistent track record of doing exactly nothing to the world's coastlines. The system has seen this movie many times, and it knows how it ends. This is what good science looks like when it works, and it is worth pausing on, because it is the opposite of the panic the automated alert might have triggered. The machine fired because it is built to be cautious, to treat every large undersea quake as a potential threat until proven otherwise, and that caution is a feature, not a flaw. But behind the machine sits a body of knowledge about how this specific ocean, this specific ridge, this specific kind of fault actually behaves, and that knowledge allowed the threat to be stood down within minutes. No coastline was ever in danger. The ocean was never going to rise. The verdict was no threat, and the verdict was correct. It is worth understanding how analysts can know the mechanism of an earthquake so quickly, because it feels almost like mind reading, and it is really just clever physics. When a fault ruptures, the seismic waves it sends out are not the same in every direction. A sliding, sideways rupture pushes the ground outward in some directions, and pulls it inward in others, in a very particular four-part pattern. By gathering the first motions recorded at seismometers all around the world, and seeing which way the ground first jerked at each one, analysts can reconstruct the orientation of the fault and the direction it slipped. They summarize the result in a diagram that seismologists affectionately call a beach ball, a sphere shaded in a pattern that instantly tells a trained eye whether the quake was a sideways grind, an upward thrust, or a downward drop. For the June 17th earthquake, that pattern pointed to strike slip, the sideways grind, which is exactly what you would expect on a ridge transform, and exactly the mechanism that cannot lift the sea. The beach ball in effect told the warning centres within minutes that there was nothing to fear. There is a second line of defence too, and it sits out in the oceans themselves. After the catastrophe of 2004, when 250,000 people died because there was no warning system in the Indian Ocean, the world invested heavily in a network of sensors designed to catch a tsunami in the act. Among them are specialised buoys tethered to pressure recorders on the seafloor, instruments so sensitive they can detect the passage of a tsunami only a few centimetres high in the open ocean as it rolls over them. If a real wave had been generated on June 17th, the system was watching for it, ready to confirm it within the hour, and it never saw one, because there was never one to see. The pressure recorders on the seafloor stayed quiet. The sea level gauges on distant shores read nothing but the ordinary rhythm of the tides. Every independent line of evidence agreed with what the beach ball had already implied within minutes of the rupture, that the seabed had ground sideways and the ocean had not been lifted. When the warning centres issued their statement of no threat, they were not silencing a real danger, they were closing the book on a danger that had never opened. I find this whole sequence quietly reassuring, in a way that has nothing to do with this particular earthquake. It is reassuring because it shows that the system we built after the failures of the past actually works. In 2004, the Indian Ocean had almost none of this. No network of warning centres covering the region, no seafloor pressure sensors, no protocol to alert the threatened coasts, and 250,000 people paid the price. What happened in the Atlantic on June 17th? An automated alert, a rapid expert analysis, a confirmation from instruments in the water, and a clear all clear within the hour, is the system those deaths forced us to build, functioning exactly as designed over an empty ocean. We will never know how many future lives that machinery will save, but nights like this are quiet rehearsals, proof that the watch is being kept. The combination is what gives the warning centres their confidence. They read the mechanism from the seismic waves, they know the history of the region, and they have eyes in the water itself. When all of that lines up to say no threat, the no threat is not a hope, it is a conclusion. I want to defend that caution, the initial alert that frightened a computer in the middle of the ocean, because in a world where these systems are sometimes mocked for crying wolf, the design is exactly right. The cost of an initial alert that gets stood down is a few minutes of concern in an operations centre, The cost of failing to alert a coastline that a real wave is approaching is measured in lives. So the system is built to flinch first and analyse second, to treat every large undersea quake as a potential threat until the physics proves otherwise. On June 17th, the physics proved otherwise quickly and decisively. The flinch was appropriate, and so was the calm that followed it. That is what a mature warning system looks like when it works exactly as intended. It is worth remembering that behind the automated system sit real people, often working through the night, who carry the weight of these decisions. An analyst at a tsunami warning centre has minutes to look at the incoming data and make a call that could mean ordering hundreds of thousands of people to flee, or deciding that no such order is needed. Issue too many warnings that come to nothing, and people stop listening, which is its own kind of danger. Fail to issue one that was needed, and the cost is unthinkable. The men and women who do this work live in that tension constantly, and the speed and confidence with which the June 17th event was assessed and stood down shows just how good they and their tools have become. A magnitude 6.6 under the ocean would have caused chaos and uncertainty a few decades ago. On this night, it was understood, evaluated, and resolved almost as fast as it was felt. And yet, here is where I have to be honest with you, because the channel does not deal in false comfort any more than it deals in false fear. Everything I have just told you about why this earthquake was harmless is true, and every piece of it is conditional. It was harmless because of how the ground moved, and where it moved, and what kind of fault it moved on. Change any one of those conditions, and the verdict changes with it. The Atlantic is not safe because it is incapable of making a tsunami. The Atlantic was safe on June 17th because of a very particular set of circumstances that happened to line up in our favour. To see how easily those circumstances can fail to line up, we have to leave the present for a moment and travel back to a November afternoon in 1929 when the Atlantic did exactly the thing everyone assumes it cannot do. But first, there is a reason this swarm was so unusually strong for where it happened, and that reason matters more than it first appears. Part 7. Why the Ridge rarely breaks this hard. There is something quietly remarkable about a magnitude 6.6 on the mid-Atlantic ridge, and to appreciate it you have to understand why this ridge almost never produces truly enormous earthquakes in the first place. The reason has to do with the nature of the crust at a spreading boundary, and it is the same reason that paradoxically makes the ridge both safe and fascinating. At a place where two plates pull apart, the crust is thin, it is hot, and it is mechanically weak. Magma sits close to the surface. The rock is young, fractured, and warm warm, weak rock cannot store very much stress before it gives way. Think of it like the difference between snapping a cold, brittle stick and trying to snap a warm, green branch. The cold stick stores up tension and then breaks all at once with a violent crack, releasing all that energy in an instant. The green branch bends and tears and gives way gradually, never building up to that single catastrophic release. The crust at a subduction zone is like the cold stick. It is cold, strong, and capable of locking up for centuries, storing colossal amounts of stress until it ruptures in a magnitude 8 or 9 that heaves the seafloor upward and sends a wall of water at a coastline. The crust at a spreading ridge is more like the green branch. It is warm and weak, it cannot lock up the same way, and so it releases its energy in smaller, more frequent events. This is why the great majority of ridge earthquakes are modest, and why the ridge, for all its size and violence, is not a great tsunami factory. Which is exactly what makes this swarm worth our attention. A magnitude 6.6 sits near the upper end of what this environment normally produces, and a tight cluster of magnitude 5 and 6 events alongside it represents a genuinely energetic burst for a spreading boundary. It is not a sign of the apocalypse. It is not a warning that the Atlantic is about to do something it has never done. But it is the ridge releasing stress in a more concentrated way than usual, and for a feature that normally murmurs, this was closer to a shout. The honest scientific reading is that the fault released accumulated strain, possibly migrating along its length as one segment loaded the next, which is exactly the kind of behaviour that produces swarms rather than a single clean main shock. Let me put a little more flesh on why the crust here is so weak, because it is the physical core of why the ridge is usually so gentle. The strength of rock, its ability to store stress before it snaps, depends enormously on temperature. Cold rock is brittle and strong, like glass, capable of holding tremendous tension, and then failing in one violent crack. Hot rock is ductile, It flows and deforms rather than snapping, and it cannot build up the stress for a great earthquake. At a spreading ridge, molten rock sits close beneath the surface, and the temperature climbs steeply with depth. The zone of cold, brittle rock that can actually generate earthquakes is therefore thin, just a few kilometers thick before you reach rock too hot and soft to break. A fault can only rupture in that thin, brittle layer, and a thin rupture zone caps the size of the earthquake. That is the underlying reason ridge quakes stay modest. There is simply not enough cold, strong rock to make a monster. It helps to remember how the magnitude scale actually works, because it changes how you hear these numbers. The scale is not linear, it is logarithmic, which means each whole step up represents a roughly 32-fold increase in the energy released. A magnitude 7 is not slightly stronger than a magnitude 6. It releases about 32 times more energy. A magnitude 8 releases about 1,000 times more than a 6. And a great magnitude 9 subduction earthquake, the kind that heaves the seafloor and drowns coastlines, releases on the order of 30,000 times the energy of the magnitude 6.6 that struck the Atlantic. So when I say the ridge produces modest earthquakes, understand the gulf I am describing. The difference between a ridgequake and a subduction megathrust is not a matter of degree, it is a matter of entire categories of violence, separated by factors of thousands. The warm, weak crust of the ridge cannot even approach that upper range. It releases its strain long before it could ever store the energy for a true monster. And that is genuinely the good news buried in this story. The Mid-Atlantic Ridge, for all its size, for all the unsettling drama of a seam tearing down the middle of an ocean, is structurally incapable of the kind of earthquake that produces the great ocean-crossing tsunamis. The crust will not let it happen. The ridge murmurs and occasionally shouts, but it cannot roar the way the Pacific Rim roars. The danger in the Atlantic, as we'll see, does not come from the ridge growing into something it cannot be. It comes from the other ways the ocean can be made to move, the vertical faults at the ridge axis, the landslides on the margins, and it comes from where, not just how hard. This is why the great majority of earthquakes along the entire 16,000-kilometre length of the Mid-Atlantic Ridge are magnitude 5 and below, why a magnitude 6 is notable, and why a magnitude 6.6 like June 17th sits near the upper ceiling of what this kind of boundary tends to produce. The very largest ridge transform earthquakes anywhere on Earth occasionally reach into the magnitude 7 range on the longest and best developed transform faults, but they almost never climb into the magnitude 8 and 9 territory that subduction zones routinely reach. Compare that to the Pacific Rim, where cold, thick oceanic crust dives beneath continents and locks up for centuries, storing the stress for the magnitude 9 megathrusts that displace the seafloor over hundreds of kilometers and breed ocean-crossing tsunamis. The ridge simply cannot play that game. Its crust is too warm, too thin, too weak to hoard that much energy. But I have to plant a flag here, because it foreshadows the danger we will return to. Not all ridge earthquakes are the sideways, transform kind. Right along the very axis of the ridge, where the crust is being stretched and pulled apart, the seabed can break in a different way, dropping downward along steep faults, the motion geologists call normal faulting. And normal faulting does move the seabed vertically. It is generally a less efficient tsunami maker than the great thrusts of a subduction zone, but it is not the harmless sideways grind of a transform. So even on this gentle ridge, the type of faulting is not fixed. It depends on exactly where along the ridge you are, and that variability is one of the levers I promised you, the levers that separate a harmless night from a deadly one. And here is how it all ties back to the spine of our story. The very property that makes this ridge break in smaller, sideways, tsunami-safe earthquakes, the warm and weak crust, the horizontal grinding of the transform faults, is the property that kept the coastlines of 3 continents out of danger on June 17th. The ridge is safe because of what it is, but the moment you take that same energy and put it somewhere with cold, strong crust, or somewhere where the shaking can knock loose a mountain of sediment, the safety evaporates, and the Atlantic has somewhere exactly like that. It has had it the whole time. To see what this earthquake could have been, we have to look at what an Atlantic earthquake of almost the same size actually did on a November afternoon to a coastline full of people. Part 8. The Afternoon the Atlantic Killed. On November 18th, 1929, the seafloor off the southern coast of Newfoundland, on a feature called the Grand Banks, lurched in a magnitude 7.2 earthquake. By itself, that quake might have been just another tremor felt by fishing communities along the Canadian coast. But this one did something that the June 17th quake did not, and could not, and the difference between them is the entire reason I am telling you this story. The Grand Banks earthquake shook loose an enormous mass of sediment that had been piled up on the edge of the continental shelf, and that sediment began to move. Hundreds of cubic kilometers of mud and sand and rock, destabilized by the shaking, slid down the slope into the abyss below in a single catastrophic landslide. And when that much material moves on the seafloor, it does the one thing that lifts the sea. It displaces water, a great deal of water, all at once. The result was a tsunami. About 2.5 hours after the shaking stopped, the ocean drew back from the shores of the Burin Peninsula of Newfoundland, and then it came back as a series of waves that in the narrow inlets and bays reached heights of up to roughly 13 meters, which is more than 40 feet of water surging into coastal villages. 28 people died. Homes were torn from their foundations and dragged out to sea. Entire communities that had stood for generations were gutted in an afternoon. This was not the Pacific. This was not a subduction zone. This was the Atlantic, the ocean we think of as the calm one, killing people with a wave born from an earthquake of magnitude 7.2, only a little larger than the one that struck the ridge in 2026 and harmed no one at all. Now hold those two events side by side, because this is the comparison that the whole video has been building toward. June 17th, 2026, magnitude 6.6, and the ocean did not stir. November 18th, 1929, magnitude 7.2, and a 40-foot wall of water killed 28 people. The difference in magnitude between them is real but modest. The difference in outcome is the difference between a non-event and a disaster. So what actually separated them? It was not size, it was mechanism and setting. The ridgequake moved the ground sideways on a sliding fault in the middle of the ocean. The Grand Banks quake triggered a massive underwater landslide on a steep, sediment-loaded slope right next to a populated coast. Same ocean. Wildly different result. And the only thing that changed was the specific way the energy was delivered to the water. Let me slow down and tell you what that evening was actually like for the people on the Burin Peninsula, because the human detail is what makes the lesson land. It was late November, already dark and cold, when the shaking was felt along the southern coast of Newfoundland. The tremor itself did some damage and frightened people, but the coast had felt earthquakes before, and many assumed the worst was over. Then, about 2.5 hours later, the sea began to behave strangely. In the narrow bays and inlets that notch that coastline, the water first drew out, exposing the harbour bottoms, and then it came back in a series of surges. Because those inlets funnel and concentrate a wave, the water in some of them rose to heights of around 13 metres, more than 40 feet, and it came in the dark with no warning of any kind. Homes were lifted off their foundations and carried out to sea, some with families still inside. Boats were thrown inland. Stores of food and supplies laid in for the coming winter were destroyed in minutes. 28 people lost their lives that night, and the survivors were left in a nightmare of isolation, because here is the cruelest detail. The same underwater landslide that generated the wave had also severed the telegraph cables that connected the region to the outside world. The communities could not call for help. For days, much of the outside world did not even know a disaster had happened. Aid was slow to arrive to a coast already poor and now stripped of its homes, its boats, and its winter provisions. The Grand Banks tsunami remains the deadliest earthquake-related disaster in Canadian history, and it happened not on some distant exotic coastline but on the shore of the North Atlantic, the ocean we keep telling ourselves is the safe one. And the mechanism is the thing to hold on to because it is the lever that matters most for our story. The magnitude 7.2 earthquake did not generate that wave by heaving the seafloor upward. It generated it by shaking loose an immense volume of sediment, hundreds of cubic kilometers of mud and sand piled up over millennia on the edge of the continental shelf, and sending it roaring down the slope into the abyss as a submarine landslide. It was the moving mass of sediment, displacing water as it slid, that lifted the sea. This matters enormously because it means an earthquake does not have to be the right type and does not even have to displace the seafloor directly to make a killer wave. It only has to shake hard enough, near enough to a loaded slope to start an avalanche under the water, and the margins of the Atlantic, where rivers have dumped sediment for millions of years, are lined with exactly those kinds of loaded slopes. The The Grand Banks disaster gave science something else too, almost as a grim consolation prize, and it is a detail I cannot resist telling you because it shows how a tragedy can illuminate the planet. As that underwater landslide raced down the continental slope, it snapped a series of transatlantic telegraph cables lying on the seafloor one after another in sequence. Years later, scientists realized that the exact times those cables broke had been automatically recorded, and by looking at when each cable down the slope failed, they could calculate how fast the underwater avalanche had travelled. The answer was staggering, speeds of over 60 miles per hour in places. That reconstruction gave birth to an entire field of study, the science of what are called turbidity currents, the underwater avalanches that shape the floor of every ocean on Earth. That discovery rewrote our understanding of the ocean floor. Before Grand Banks, no one fully grasped that underwater avalanches of sediment could travel so far and so fast, or that they were a primary force shaping the abyss. The cables, breaking in sequence down the slope, were an accidental experiment that revealed a hidden world of motion at the bottom of the sea, and the scientists who later studied those break times, including the same researchers who would go on to map the mid-Atlantic ridge itself, founded the study of turbidity currents on the back of that tragedy. It turns out that these underwater avalanches have been carving canyons and building enormous fans of sediment across the floor of every ocean for as long as there have been oceans. The Atlantic, in killing 28 people, also taught us how the seabed itself is sculpted. But the lesson that matters for us tonight is simpler and colder. The Atlantic can make a killer wave. It has done it within living memory, and it did not need a monster earthquake to do it. Part 9. The Wave That Crossed an Ocean. If 1929 shows that the Atlantic can kill with a landslide near a coast, then I have to take you back further, to a morning that has haunted Europe for almost 3 centuries, to show you that the Atlantic can also send a wave clear across itself. On the 1st of November, 1755, a colossal earthquake, estimated by modern researchers at somewhere around magnitude 8.5 or larger, struck in the Atlantic offshore of Portugal. The city of Lisbon was devastated by the shaking, and then, while survivors gathered in the open spaces near the waterfront thinking themselves safe, the sea drew back and returned as a tsunami that swept through the lower city. Tens of thousands died across Portugal, Spain and Morocco, and the waves did not stop at the edge of the eastern Atlantic. They radiated outward across the entire ocean, and hours later they were recorded on the far side, reaching the islands of the Caribbean with measurable, in places destructive, surges. The Lisbon earthquake happened in a completely different tectonic setting from the mid-Atlantic ridge. It struck near the boundary between the African and Eurasian plates, a zone of compression and complex faulting off the Iberian coast, the kind of place where the seafloor can be heaved upward in the vertical motion that breeds great tsunamis. That is precisely the point. The Atlantic is not a single uniform thing. Most of it along the ridge breaks in the gentle, sideways, tsunami-safe way we have been describing. But around its edges, at its margins, where it meets the continents and where old or complex plate boundaries lurk, the Atlantic is fully capable of generating a wave that crosses the entire ocean and arrives on a distant shore with enough power to be remembered for 250 years. The detail of that morning is worth telling because it shows how an Atlantic tsunami can arrive as part of a cascade of horrors. The 1st of November is All Saints' Day, and in 1755 the churches of Lisbon were packed with worshippers, candles lit by the thousands. When the earthquake struck in mid-morning, the shaking brought down churches and homes across the city, and the toppled candles set fires that would burn for days. Survivors fled the collapsing, burning streets toward what seemed like the one safe open space, the broad waterfront along the Tagus River where it meets the sea. And there, they watched the water pull back, draining the harbour and exposing old shipwrecks and lost cargo on the bare riverbed. Then it returned. A tsunami swept up the river and across the lower city in a series of waves, drowning many of the very people who had fled there to escape the rubble and the flames. Earthquake, then fire, then flood. 3 disasters stacked into a single morning, killing tens of thousands across Portugal and reaching down the coasts of Spain and Morocco. And the waves did not respect the size of the ocean. They radiated outward across the entire Atlantic, and hours later they were observed and recorded on the far side, with surges reported in the Caribbean strong enough to be noticed, and in places to do damage. A wave borne off the coast of Portugal reached the islands of the Americas the same day. That is the reach of an Atlantic tsunami when the conditions are right, when a large earthquake near a continental margin heaves the seafloor in the vertical way that lifts the entire ocean. The Lisbon disaster so shook the educated world that it changed European thought, prompting philosophers to wrestle with how such suffering could occur and prompting the first organized scientific attempts to understand and respond to earthquakes. In a real sense, modern seismology and modern disaster management were born from the trauma of a single Atlantic morning. What I want you to take from Lisbon, beyond the horror, is the proof of reach. A tsunami born on one side of the Atlantic was felt on the other side the same day. That is not a property of the Pacific alone. It is a property of any large enough vertical displacement in any large enough body of water, and the Atlantic is plenty large enough. The only reason we do not live in fear of Atlantic tsunamis the way some Pacific coastlines do is that the conditions to make them are rarer here, not absent. The ridge down the middle, as we have seen, is the gentle part, the sideways grinding part. But the edges of the Atlantic, the continental margins and the few subduction zones tucked into the Caribbean and the far south are a different matter entirely, and Lisbon is the reminder carved into history of what those edges can do. So when you hear that the June 17th earthquake posed no threat, hold it next to Lisbon and Grand Banks in your mind, and let both truths sit there together without cancelling each other out. This particular quake was harmless, genuinely and provably harmless, and the ocean it happened in has, within recorded history, killed tens of thousands of people with waves of its own making. Both things are true. The art is in understanding why this one fell on the harmless side of the line, and that is exactly the understanding this story is built to give you. So let me weave this back into the thread, because it would be easy to hear about Lisbon and feel only fear, and fear is not the point. The point is precision. 1755 was a different mechanism, a vertical heave in a different place, a continental margin than June 17th, which was a sideways slide on a mid-ocean ridge. The reason 2026 produced no wave and 1755 produced a catastrophe is not luck, and it is not mystery. It is the same set of variables we have been tracking the entire time. Mechanism, location, the direction the ground moves. Get those variables one way, and a magnitude 6.6 is a non-event in the middle of nowhere. Get them another way, and the Atlantic reaches across itself to drown cities it has never seen. This is what I mean when I say the implication of the June 17th earthquake is quiet and conditional. The quake itself threatened no one. But it is a reminder, written in fresh seafloor, that the ocean basin we treat as safe contains within it every ingredient needed for disaster, waiting only for the variables to align. So the real question, the one worth 2 hours of your evening, is not whether the Atlantic can make a tsunami. We have just proven that it can, twice, with real bodies and real dates. The real question is what exactly would have to be different about an earthquake like the one on June 17th for the answer to flip from no threat to run. And the answer to that is more specific and more sobering than you might expect. Part 10. The terrifying implication spelled out. Let me now do the thing the title of this video promised, and spell out the implication plainly, without exaggeration and without flinching, because you have earned the honest version. The earthquake on June 17th was harmless, but it sat at the intersection of conditions that, if shifted only slightly, would not have been harmless at all. There are essentially 3 levers, and the planet held all 3 in the safe position that night. The unsettling part is how easily, in the right place, each one can be thrown the other way. The first lever is the mechanism. This quake was strike-slip, a sideways grind which lifts almost no water. But the mid-Atlantic ridge is not made only of transform faults. Along the ridge axis itself, the crust is being stretched and pulled apart, and that stretching produces what are called normal faulting earthquakes, where a block of the seabed drops downward along a steep fault. A normal faulting event does move the seafloor vertically, and a large enough one in the right spot can displace water. The motion is generally less efficient at making tsunamis than the great upward heaves of subduction zones, but it is not nothing. Change the mechanism from sideways grinding to vertical dropping, and you have begun to lift the sea. The second lever is the landslide, and this is the one that should genuinely give you pause, because we have already seen it kill. The floor of the Atlantic, especially along the continental margins where sediment piles up over millions of years, is loaded with unstable slopes. A strong earthquake near one of those slopes does not need to lift the seafloor itself at all. It only needs to shake hard enough to knock that sediment loose, and gravity does the rest. The landslide displaces the water. That is exactly what happened on the Grand Banks in 1929, with an earthquake only slightly larger than the one in 2026. The ridge swarm happened far from any such slope, in the bare middle of the ocean. But the same magnitude of shaking delivered near the edge of a continent, near one of those sediment-loaded margins, is a fundamentally more dangerous thing. The third lever is location, and it is the one that turned June 17th from a possible headline into a footnote. This earthquake happened more than 1,000 miles from anyone. Any energy it might have put into the water had the entire width of an ocean to dissipate before reaching a shore. But the mid-Atlantic ridge runs the full length of the Atlantic, and parts of it pass far closer to inhabited coastlines, near the Azores, near Iceland, near the approaches to Europe and the islands of the central Atlantic. An earthquake of this same character, closer to one of those places, would give a wave far less room to fade. Pull the location lever, and distance stops protecting anyone. There is a sobering way to think about this over the long run, and it has nothing to do with panic. On any single night, the odds that all three levers fall the dangerous way at once, in a populated place, are very low, which is why disasters like Grand Banks and Lisbon are spread across centuries rather than years. But geology does not work on human timescales. Over decades and centuries, the Atlantic will keep producing earthquakes, keep loading its sediment slopes, keep grinding its margins, and somewhere, eventually, the levers will align the wrong way again, as they have before. This is not a prophecy of doom. It is simply how a living planet behaves. The right response is not fear, but preparation. The same unglamorous work that has saved lives elsewhere, mapping the unstable slopes, maintaining the warning networks, teaching coastal communities that the sea pulling back is a signal to move to high ground. The June 17th earthquake threatened no one, but it is a free reminder, delivered at no cost in lives, that the Atlantic deserves the same respect we give the Pacific. Let me push on the landslide lever a little harder, because the historical record of the Atlantic contains a warning even larger than Grand Banks, and most people have never heard of it. Around 8,000 years ago, off the coast of Norway, a stretch of the seafloor the size of a small country gave way in one of the largest submarine landslides known to science, an event called the Storegga Slide. An almost unimaginable volume of sediment slid down the continental slope into the abyss, and it displaced so much water that it sent a tsunami racing across the North Atlantic. That wave struck the coast of Scotland, where geologists today still find its sand layer pushed far inland, and it is thought to have helped finish off Doggerland, the low-lying land bridge that once connected Britain to mainland Europe, drowning it beneath the North Sea. There were no cities then to record the death toll, but had it happened today, it would rank among the great natural disasters imaginable. The Atlantic did that, not the Pacific, not some distant exotic sea, the same ocean that lapped harmlessly above the ridge on June 17th. And here is something most people never learn in school. The Atlantic does have subduction zones after all, just not many, and they hide at its edges. In the eastern Caribbean, the Atlantic seafloor is slowly diving beneath the arc of islands that runs from Puerto Rico down through the Lesser Antilles, and just north of Puerto Rico lies a trench that plunges to around 8,400 meters, the deepest point in the entire Atlantic Ocean. That subduction zone is fully capable of the vertical megathrust-style ruptures that breed great tsunamis, and history proves it. In 1867, a quake near the Virgin Islands sent a tsunami through the eastern Caribbean, and in 1918, an earthquake off Puerto Rico generated a wave that killed dozens along its coast. Far to the south, another small subduction zone curls around the South Sandwich Islands. We have explored the Lesser Antilles boundary on this channel before precisely because it is the Atlantic's most overlooked tsunami threat, a real subduction zone in an ocean everyone assumes has none. Even the passive, quiet margins carry the danger in the form of sediment. Off the eastern seaboard of the United States, where there is no subduction zone at all, the continental slope is piled high with sediment delivered by rivers over millions of years, and geologists have mapped the scars of enormous prehistoric submarine landslides there, features with names like the Currituck Slide off the Virginia and Carolina coast. If a large enough earthquake, or even the slow pressure of accumulating sediment, were to set one of those slopes moving again, the resulting wave would not have an ocean to cross. It would be born right at the doorstep of some of the most densely populated coastline in North America. That is the landslide lever and the location lever combined, sitting quietly off a coast that thinks of tsunamis as someone else's problem. So when I lay out the three levers, understand that each one is not a hypothetical. Each is something the Atlantic has actually done. The mechanism lever, vertical faulting instead of sideways grinding, is what Lisbon shows. The landslide lever, shaking loose a loaded slope, is what Grand Banks and Storegga show. And the location lever, the difference between the empty middle and a populated margin, is the difference between an event no one feels and an event that ends up in the history books. On June 17th, all three levers sat in the safe position. The faulting was sideways, not vertical. No major slope was nearby to be shaken loose, and the spot was as far from people as the ocean gets. Pure circumstance, all three at once in our favour. But the mid-Atlantic ridge does not stay in the empty middle. It runs the entire length of the ocean, and in places it passes close to inhabited land. Near the Azores, the ridge and its associated faults sit beneath populated islands that have suffered destructive earthquakes in their history. Far to the north, the ridge runs straight through Iceland, which is in effect a piece of the mid-Atlantic ridge that has grown large enough to stand above the waves, with all the seismic and volcanic restlessness that implies. And all along the eastern seaboard of the Americas and the western coast of Europe and Africa, the continental margins hold their piled sediment on slopes that a strong, well-placed earthquake could destabilize. The geography that protected us on June 17th is not a permanent shield. It is a roll of the dice that happened to come up safe. So here is the implication, stated as plainly as I can state it, and tied back to everything we have built. The June 17th earthquake was not a threat, and I want to be absolutely clear that no warning was issued and no coast was ever in danger. But it was a demonstration. It showed us, in real time, the energy that the seam of the Atlantic can release. And the only reasons that energy stayed harmless were the mechanism, the absence of a landslide, and the sheer remoteness of the spot. Throw any one of those three levers the other way, normal faulting instead of strike slip, a sediment slope instead of bare ridge, a populated margin instead of the empty middle, and the Atlantic becomes capable of doing to a modern coastline what it did to Newfoundland in 29 and to Lisbon in 55. The ocean we call safe is not safe by nature. It is safe by circumstance, and circumstances change. That is the terrifying implication, and it is quiet precisely because it asks you to think instead of panic. But there are louder voices that take a night like this and twist it into something it is not, and before we close I have to deal with them, because the truth deserves to be defended from the myths that cluster around it. Part 11. What the swarm is actually saying. Before we get to the myths, I want to return to the swarm itself because there is a language to the way earthquakes cluster, and once you learn to read it, the events of June 17th and 18th tell a coherent and rather elegant story. Earthquakes almost never come as a single isolated shock. They come in families, and the relationships within those families follow rules that scientists worked out more than a century ago. There is a pattern to how a fault releases its energy, and that pattern is the closest thing we have to the planet speaking out loud about what is happening kilometers below the seafloor. The first rule is one you can feel intuitively. The bigger an earthquake is, the rarer it is. For every magnitude 6, there are roughly 10 magnitude 5s and 100 magnitude 4s, and so on down the scale. This relationship is so reliable that when seismologists look at a sequence of quakes, they can tell whether it is behaving normally or whether something unusual is going on simply by counting the events at each size. The June sequence, a single 6.6 riding above a cluster of 5s, fits the shape of a fault releasing a concentrated burst of strain. The second rule concerns what follows a large quake. Aftershocks tend to be smaller than the main shock by a fairly consistent margin, with the largest aftershock typically running more than a full magnitude unit below the main event. For a 6.6, that points to a largest companion in the mid-5 range, which is almost exactly what the Atlantic produced. The planet, in other words, behaved by the book. But there is a wrinkle that makes this particular sequence more interesting than a textbook example, and it goes back to the word swarm. In a classic main shock and aftershock sequence, one dominant quake is clearly the boss, and everything after it is a fading tail. In a swarm, the events are more democratic, several of them of comparable size, with no single shock obviously in charge. Swarms often happen where fluids are moving through the crust, or where stress is migrating along a fault, one patch of rock failing and loading the next patch beside it, which then fails and loads the next. On a mid-ocean ridge, With magma and hot fluids close to the surface, and with the crust constantly being pulled apart, the conditions for swarm behaviour are practically built in. The most likely reading of June 17th is a pulse of strain release that walked along a segment of the ridge or its transform, each rupture handing off to the next, like a row of latches popping open one after another. There is an extra ingredient at a mid-ocean ridge that makes swarms especially common here, and it is fluid. The ridge is not just rock under stress, it is rock laced with heat and water. Seawater seeps down through cracks in the young crust, gets superheated near the magma below, and circulates back up, and along the way it changes the pressure inside the faults. Fluid moving through a fault can act almost like a lubricant, lowering the friction that holds the two sides locked, and a pulse of fluid migrating along a fault zone can set off a string of earthquakes as it goes. This is one of the reasons ridges and their transforms produce swarms rather than tidy single main shocks more often than many other settings do. The dune sequence carries the fingerprints of exactly this kind of process: strain and possibly fluids working their way along a segment, releasing in a cluster rather than a single clean break. None of which, and this is the point I keep returning to, points towards something worse on the horizon. A swarm driven by strain release and fluid migration on a spreading ridge is the boundary doing its ordinary work, the work of pulling an ocean apart compressed into a noisy few hours. It is not a countdown, it is not a build-up, it is the planet exhaling. I want to anchor this somewhere you can picture, because the middle of the equatorial Atlantic is hard to hold in your mind. Not far from where this swarm struck, the mid-Atlantic ridge does something it almost never does anywhere else, along its 16,000 kilometers. It breaks the surface. A tiny cluster of barren, jagged rocks called the St. Peter and St. Paul archipelago juts out of the open ocean near the equator, a handful of stony islets battered by waves 1,000 miles from any continent. Those rocks are one of the only places on the planet where you can stand on the actual crest of the mid-ocean ridge system in the open Atlantic, where the seam that manufactures the seafloor pokes its head above the water. When I tell you the earthquake happened on the ridge, that is the kind of place I mean, a place where the raw machinery of the planet is close enough to touch. And the swarm was the machinery doing exactly what it has done for 180 million years, releasing the strain of a widening ocean, this time in a burst loud enough to make the instruments jump and the automated systems flinch. If you have watched the channel over the last couple of nights, these rules will sound familiar because we leaned on the very same ones to read the earthquakes hitting Asia, and that is the point. The laws that govern how earthquakes cluster are universal, whether the fault is a subduction megathrust in the Pacific or a transform on the floor of the Atlantic. The relationship between the size of quakes and how often they occur was worked out by two seismologists, Gutenberg and Richter, the same Richter whose name became attached to magnitude. The decay of aftershocks over time was described even earlier by a Japanese researcher named Omori, whose law still holds more than a century later, and the rule that the largest aftershock tends to run a bit more than a magnitude below the main shock carries the name of the seismologist Barth. These are not vague tendencies, they are some of the most reliable statistical patterns in all of Earth science, and the Atlantic swarm obeyed them faithfully. There is one question these laws cannot answer, though, and it is the question that haunts seismology. In the moment, you cannot tell a foreshock from an ordinary earthquake. The magnitude 6.6 could, in principle, have been a foreshock to something larger, because that is only ever knowable in hindsight. If a bigger quake had followed, we would have relabeled the 6.6 as its foreshock. Since no bigger quake followed, it stands as the main shock of a swarm. This is not a failure of science so much as a hard limit of it, and it is the same uncertainty that hangs over every significant earthquake the moment it happens, including the ones we have been tracking in the Pacific. The honest position is that the behaviour of the Atlantic sequence, several events of similar size with no single dominant shock and no escalation, fit a swarm releasing strain rather than a build-up towards something larger. The ridge was letting go, not winding up. Let me linger on those rocks near the equator, the St. Peter and St. Paul archipelago, because they are one of the genuinely extraordinary places on the planet and they make this abstract ridge concrete. They are a tiny cluster of stark white-stained islets, barely rising above the waves, more than 900 kilometers from the Brazilian coast, the only spot in the entire equatorial Atlantic where the mid-ocean ridge system breaks the surface. They are so remote and so geologically strange that when a young naturalist named Charles Darwin passed by aboard the Beagle in the 1830s, he stopped to examine them and puzzled over their odd composition, which, unlike most ocean islands, is not volcanic but is mantle rock shoved up to the surface along the ridge. To stand on those rocks is to stand on the exposed bones of the planet's spreading engine, and the earthquake of June 17th happened in their neighbourhood, on the same restless seam, the machinery doing in the dark what those rocks reveal in daylight. There is something humbling in that image, of a handful of bare rocks in the middle of the ocean, marking the one visible point of a structure that stretches unseen for thousands of miles in both directions. They are the tip of something almost too large to picture, the exposed knuckle of a planet in motion. Sailors have known those rocks for centuries as a hazard and a curiosity, never realizing they were standing on the crest of the engine that built the entire ocean around them. We know now, and knowing turns a swarm of earthquakes near those rocks from a frightening headline into a window onto the living architecture of the Earth. So the swarm itself is not a warning of something worse to come. It is the ordinary made briefly visible, the slow and constant tearing of the Atlantic expressing itself in a concentrated few hours. And that is precisely why it is worth understanding rather than fearing, and precisely why it is so frustrating when the event gets hijacked by claims that have nothing to do with the physics. Because the moment a large earthquake happens anywhere, a chorus rises up to explain it with everything except the actual cause, and the loudest of those voices reaches all the way to the Canary Islands, to a volcano that supposedly threatens to drown the eastern seaboard of the United States. That claim deserves a careful, honest hearing, and then it deserves to be taken apart. Part 12. The Myth of the Wave That Eats Cities. There is a story that circulates every time the Atlantic so much as twitches, and it goes like this. On the island of La Palma in the Canary Islands sits a volcano called Cumbre Vieja, and one day, the story claims, an eruption will cause the entire western flank of that volcano to slide into the sea all at once, a single titanic block of rock, and that collapse will send a wave hundreds of feet high, racing across the Atlantic to obliterate New York, Boston, and the whole eastern seaboard of the United States. It is a vivid, cinematic, genuinely frightening idea. It has been featured in documentaries and repeated across the internet for over 2 decades, and the scientific consensus is that it is, in its dramatic form, almost certainly wrong. The idea traces back to a single study published around the year 2001, which modelled a worst-case scenario in which an enormous coherent block of the volcano detached and entered the ocean in one motion. The problem is nearly everything about that scenario. Geologists who have studied the actual collapse deposits around volcanic islands find that these flank failures do not tend to happen as a single clean block. They happen in stages, in pieces, over time, and a collapse that breaks apart as it falls puts far less energy into the water than the all-at-once model assumed. Beyond that, the modelling of how such a wave would travel has been revisited repeatedly, and the consistent finding is that even a large flank collapse would produce waves that lose enormous height as they cross thousands of miles of open ocean, arriving at the far shore as something serious for local coasts near the Canaries perhaps, but nothing remotely like the continent-erasing wall of the legend. It is worth noting what happened when the volcano actually erupted, because reality ran a kind of test of the legend. In the autumn of 2021, Cumbre Vieja erupted for the better part of 3 months, pouring out lava that buried homes and farmland and reshaped part of the island. It was a serious eruption with real human cost for the people of La Palma, and the western flank did not slide into the sea. There was no mega tsunami, no continent-erasing wave, not even a hint of one. That single real-world episode does not prove such a collapse can never happen on a geologic timescale, but it punctures the breathless framing that treats it as imminent. The careful science had said the doomsday version was overblown, and when the volcano finally roared, the careful science was vindicated. I bring this up not to mock anyone who is worried about it, because it is a genuinely compelling story, and it was seeded by a real scientific paper. I bring it up because it is the perfect mirror image of what we have been discussing all night. The Cumbre Vieja mega tsunami is Atlantic tsunami fear inflated to the point of fantasy, a real mechanism, flank collapse stretched into a doomsday that the evidence does not support, and the June 17th earthquake is the opposite mistake waiting to happen, a real event that could be inflated into a threat it never posed. There is a pattern to how these inflations work, and once you see it, you can spot it everywhere. A real mechanism gets identified, a flank collapse, an earthquake, a swarm. Then the most extreme imaginable version of it gets treated as the likely version. Then the careful qualifications, the staged collapse instead of the single block, the dissipating wave instead of the continent killer, the sideways grind instead of the vertical heave, get stripped away because they are less dramatic and harder to fit in a thumbnail. What remains is a story that is technically rooted in something real, but has been stretched into something false. The defense against it is not cynicism, it is curiosity, the willingness to ask what the actual evidence says rather than accepting the most frightening version on offer. That is the entire posture of this channel, and it is why we can look at a tsunami alert in the middle of the Atlantic and neither dismiss it nor catastrophize it, but understand it. The honest path runs between the two. The Atlantic can make tsunamis, as Newfoundland and Lisbon prove. The Atlantic is not going to be erased by a single mythical wave from a single volcano, as the careful science shows. And tonight's earthquake was neither the apocalypse nor nothing, but a precise demonstration of conditional risk. Hold that balance, because the next myth is even more seductive, and it points not at a volcano, but at the sun. Part 13. No, the sun did not do this. Every time the ground moves, somebody insists the sun did it. The claim is that solar activity, geomagnetic storms, solar flares, the eruptions of charged particles that occasionally slam into our planet, somehow trigger earthquakes, and that if you watch the sun closely enough you can predict when the earth will shake. It is an appealing idea because it connects two of the most dramatic forces in nature, and because it offers the tantalizing promise of prediction. And on the night of June 17th, the data does something beautiful to this claim. It demolishes it, cleanly, with the simplest possible evidence. Here is what the sun was actually doing when the Atlantic seabed tore open. Almost nothing. The space weather conditions in the days around the earthquake were quiet, about as quiet as they get. The planetary index that measures geomagnetic disturbance was sitting near the bottom of its scale, peaking around 2 on a scale that runs to 9. There were no major solar flares, only the lowest, weakest class of activity. There were no large eruptions of solar material aimed at the Earth, none of the coronal mass ejections that drive the real geomagnetic storms. The sun was calm, and yet the Earth produced a magnitude 6.6 and a swarm of strong aftershocks anyway. If a quiet sun can sit overhead while the seafloor ruptures, then solar activity cannot be the thing pulling the trigger. The simplest version of the solar earthquake theory requires the sun to be active when the ground breaks, and on June 17th the sun was about as inactive as it ever is. This is the part of the channel where I always try to be fair to the underlying intuition, because the intuition is not stupid. The Earth is genuinely connected to the sun in countless ways, and it is reasonable to wonder whether the same forces that paint auroras across the sky could also nudge a fault. But wondering is not the same as demonstrating, and when researchers have looked hard for a reliable statistical link between solar activity and global earthquakes, they have not found one that holds up. The energy that drives earthquakes comes from inside the Earth, from the slow churning of the mantle and the grinding of the plates, forces vastly larger than the gentle electromagnetic tug of a solar storm. The Atlantic swarm was driven by the stress of a widening ocean, the same engine we have been describing all night, not by anything happening 93 million miles away. The seam tore because the seam is always being pulled apart, and on this night the strain simply found its release. There is one cousin of this idea that does have a sliver of scientific support, and being fair means mentioning it. The gravitational pull of the moon and the sun raises tides not just in the ocean but in the solid rock of the Earth itself, flexing the crust very slightly twice a day. Researchers have found faint statistical hints that, for certain faults already on the very edge of failure, these tiny tidal stresses might marginally influence the timing of when they finally slip. But notice how different that is from the popular claim. It is the gravitational tide, not solar flares or geomagnetic storms, and the effect is minuscule, a subtle nudge to the timing of a quake that was going to happen anyway, never a cause that can be used to predict anything. The energy in a solar storm reaching the Earth is trivial compared to the forces locked in a fault. The auroras a solar storm paints across the sky are spectacular, but they are a feather landing on a boulder that is already teetering. On June 17th, even that feather was absent, because the sun was quiet and the boulder went over anyway. I understand the appeal of wanting the sun to be the cause, because it would mean the chaos is predictable, that if we just watched the sky carefully enough we could know when the ground would move. The hard truth that seismology has had to make peace with is that earthquakes remain fundamentally unpredictable in the short term. We can map where they are likely over decades, we can calculate the long-term odds on a given fault, but we cannot tell you that a specific quake will strike on a specific day, and no reliable signal, solar or otherwise, has ever been found that lets us do so. That is uncomfortable, and it is exactly why the false certainty of the solar earthquake claim is so seductive and so worth resisting. The honest position is humbler and harder. The Earth releases its strain on its own schedule, driven by forces inside itself, and the best we can do is understand the machinery and keep watch, which is precisely what happened on June 17th. So we can set the sun aside, the way we set aside the Canary Islands, and return to the one connection that is genuinely worth taking seriously. Because unlike the others, it rests on real, documented physics. It is the possibility that the Earth, on June 17th, was talking to itself, that a violent sequence on one side of the planet might have whispered to a fault on the other. We have been covering exactly such a sequence in the Pacific over the last several nights, and the timing is hard to ignore. So let us ask the question honestly, can one earthquake, on the far side of the world, help set off another? Part 14. A conversation across the planet. While the Atlantic was tearing along its seam, the other side of the planet was in open revolt. The Pacific Ring of Fire, that great horseshoe of subduction zones where most of the world's largest earthquakes are born, had been unusually loud, with a powerful sequence in the southern Philippines that we have followed closely on this channel over the last several nights, including a magnitude 7.8 and a long train of strong aftershocks. And so it is completely natural, looking at a map with the Pacific erupting on one side and the Atlantic swarming on the other, to ask whether they could be connected. It is one of the most seductive questions in earth science, and it deserves a careful answer rather than a dismissive one, because the truth is more interesting than either a flat no or a breathless yes. There are two ways earthquakes can influence other earthquakes, and the distinction is everything. The first is called static stress transfer. When a fault ruptures, it changes the stress on the rock around it, nudging nearby faults closer to or further from failure. This effect is real and well documented, but it falls off rapidly with distance. It can explain why one earthquake triggers aftershocks tens or even a couple of 100 kilometers away. It cannot reach across an entire planet. The Pacific and the equatorial Atlantic are separated by thousands of miles and by the entire bulk of the Earth. Static stress transfer between them is simply not physically plausible. On that mechanism, the two sequences are strangers. The second mechanism is more subtle, and it is the one that keeps the question alive. It is called dynamic triggering. When a very large earthquake occurs, it sends seismic waves rolling through and around the entire planet, and those waves, as they pass through a distant fault that is already loaded and near its breaking point, can in rare, documented cases give it the final nudge it needs to slip. This is real. It has been observed, for example, after some of the largest earthquakes of the past few decades, where distant faults showed small bursts of activity as the seismic waves swept through. So the honest answer to whether the Pacific could have influenced the Atlantic is not no. It is that dynamic triggering is physically possible, but it is unproven for this specific pair of events, and it should be treated as an open question, not a conclusion. The reason dynamic triggering is taken seriously at all is that it has genuinely been caught in the act, in a handful of famous cases. When a large earthquake struck Landers, California in 1992, seismologists noticed small bursts of seismic activity light up at distant sites across the western United States in the hours that followed, as its surface waves rolled through. When the Great Denali earthquake struck Alaska in 2002, it appears to have set off small quakes as far away as Yellowstone, thousands of kilometers distant, as its waves passed beneath the geyser fields. And one of the largest strike-slip earthquakes ever recorded, a magnitude 8.6 in the Indian Ocean in 2012, was followed by a measurable global uptick in seismicity for days afterward. So the phenomenon is real. Big earthquakes can, on rare occasions, nudge faults on the far side of the world that were already poised to slip. But notice the key qualifier in every one of those documented cases. The triggering earthquake was enormous, magnitude 8 or larger, and the triggered events were tiny, the faint twitches of faults already at the breaking point. Nothing about the recent Pacific sequence comes close to the scale that produces clear global triggering, and the Atlantic swarm was a robust set of magnitude 5 and 6 events, not the faint twitch you would expect from a distant nudge. There is also the simple matter of probability. The planet produces well over 100 earthquakes of magnitude 4.5 or greater every single week, scattered across the globe. With that many events happening all the time, two notable sequences overlapping in time on opposite sides of the world is not a smoking gun. It is what you would expect from chance alone, week after week. Our minds are pattern-finding machines, and that is usually a strength, but it betrays us here. Shown two dramatic events on a map, we instinctively draw a line between them, because a connected world feels more comprehensible than a random one. The discipline of science is in large part the discipline of resisting that instinct until the evidence earns it. And in this case, the evidence does not earn it. The Atlantic was pulling itself apart along its own seam, on its own schedule, for its own reasons, and the Pacific was doing the same on the far side of the planet. Two restless boundaries, one restless planet, no hidden hand required. And here is where intellectual honesty matters most, because this is exactly the kind of connection that is easy to abuse. It would be easy to point at the map and declare that the Earth is coordinating its earthquakes, that some grand pattern is unfolding, that the planet is building towards something. The data does not support that, and I am not going to pretend it does. The most likely explanation is that these are independent releases on completely different kinds of plate boundaries that happen to overlap in time, because on any given week the planet is producing dozens of significant earthquakes, and coincidences are the rule, not the exception. The remote possibility that a passing seismic wave gave the Atlantic ridge a tiny nudge is worth keeping in mind, but it changes nothing about the central story. The Atlantic swarm was driven by the Atlantic's own slow tearing, and whether or not a whisper crossed the planet, the seam was going to release that strain regardless. Which brings us finally back to the seam itself, and to what it really means to live on a planet whose oceans are alive. Part 15. The Living Seam. Let me bring us all the way back to where we started, to that lonely point in the middle of the Atlantic where the floor of the sea tore open on the night of June 17th, and to the alert that fired and then fell silent. We can see the whole shape of it now, a magnitude 6.6, riding above a swarm of strong aftershocks on the longest mountain range on Earth, at the seam where the ocean manufactures new crust. An automated system built to be cautious flinched and asked whether a wave was coming, and the planet, through the physics written into the rock, answered no, because the ground had moved sideways instead of up, on a sliding fault, in the emptiest water on the globe. No warning, no coast in danger, no threat to anyone. That answer was correct, and it was never in doubt for long. But we have learned tonight that the answer was conditional, and that is the thing I want to leave you with, because it changes how you see an entire ocean. The Atlantic did not stay calm because it is incapable of fury. It stayed calm because three things happened to line up in our favour: the sideways mechanism, the absence of a landslide, and the sheer remoteness of the spot. We have seen, in Newfoundland in 1929, what happens when a quake only slightly larger shakes loose a mountain of sediment beside a populated coast. We have seen, in Lisbon in 1755, what happens when the seafloor heaves upward near a continental margin and sends a wave clear across the ocean. The ingredients for catastrophe are all present in the Atlantic, scattered along its margins and its slopes and its ridge. On June 17th they simply did not assemble. On another night, in another place, they could. There is something genuinely strange about standing on the edge of a continent and looking out at the Atlantic, that supposedly gentle ocean, knowing what is happening at its bottom. The seam down its middle is pulling apart by the width of a fingernail every year, and has been for longer than mammals have existed. Its floor is sliced by faults 900 kilometres long that grind past each other in the dark. Its margins are piled with sediment poised on the edge of slopes that one good shake could send tumbling into the abyss. The ocean is not a still thing resting in a basin. It is a living seam, in constant slow motion, mostly murmuring, occasionally shouting, and almost always doing it where no one is there to hear. June 17th was one of those shouts, and we only noticed because we have wrapped the planet in instruments sensitive enough to catch a tremor 1,000 miles from anyone. If you remember nothing else from tonight, remember the three levers, because they are the cleanest way to think about every undersea earthquake you will ever hear about. Ask how the ground moved, sideways or up and down. Ask whether there was a loaded slope nearby to be shaken loose, and ask how far the spot was from anyone who could be harmed. Those three questions, the mechanism, the landslide potential, and the location, We'll tell you more about whether a quake is dangerous than the magnitude number that the headlines fixate on. A magnitude 6.6 sounds frightening, and on June 17th it was harmless, because all 3 levers fell the safe way. A magnitude 7.2 sounds only slightly worse, and in 1929 it killed 28 people, because one lever, the landslide, fell the other way. The number is not the danger. The geometry is the danger. And there is a strange comfort, and a stranger wonder, in understanding that. The ridge that shook on June 17th is not a monster lurking to destroy us. It is the engine that built the ocean, the seam where the planet renews its own surface, the slow and patient force that has been pushing the Americas away from Europe and Africa since before the first flowers bloomed. Every continent you have ever stood on is riding on plates that this kind of seam set in motion. The same process that frightened a computer in the middle of the night is the process that made the world map you grew up with, and that is quietly redrawing it for whoever comes long after us. To understand the ridge is to feel, for a moment, the planet breathing on a timescale that makes a human life look like a single frame in a film that has been running for billions of years. Think about what that seam has witnessed in its slow widening. When the mid-Atlantic ridge first began tearing the supercontinent apart, there was no Atlantic Ocean at all, only a narrowing rift between lands that would become the Americas on one side and Europe and Africa on the other. The dinosaurs were still alive. The ridge has been spreading, fingernail by fingernail, for so long that it opened an entire ocean from a crack, while life on land rose and fell through age after age. The water you picture when you think of the Atlantic, all of it, every wave and current and storm sits in a basin that this seam pried open one earthquake at a time. The swarm of June 17th was a few of those increments, a handful of the countless small releases that, summed over 180 million years, became an ocean. We happened to be listening for this particular handful, and for a few minutes it frightened a machine. That, in the end, is the strange gift of a night like this. An alert fires, a fear spikes, and then, if you follow it down past the headline and into the rock, the fear turns into something else, something closer to perspective. We live on a thin, cooling crust over a planet that is still vigorously alive, and most of the time we're allowed to forget it. An earthquake in the middle of the ocean is the planet briefly reminding us, and the reminder does not have to be terrifying once you understand what it is saying. It is saying that the Earth is in motion, that the oceans are not still, that the map is not finished. And it is saying that the difference between a quiet night and a catastrophe can come down to a few meters of rock moving the wrong way in the dark, which is reason enough to keep watching, and reason enough to keep trying to understand. That is why the channel exists in a way. Not to frighten you about the next disaster, but to take the things that flash across the news as a moment of alarm, a tsunami alert, a swarm in the middle of nowhere, and to follow them down to the machinery underneath, where the fear gives way to something steadier and more lasting, which is understanding. The Atlantic did not rise on June 17th. Now you know exactly why, and you know exactly what it would have taken for the answer to be different. That knowledge is worth more than the momentary jolt of the word tsunami, because it stays with you the next time the ground moves somewhere under the sea, and the headlines panic, and you find that you can read the event for what it actually is. And maybe that is the real meaning of a night like this. Not that we are in danger, because we were not, but that we live on the thin skin of a planet whose oceans are alive in ways we rarely let ourselves think about, and that the difference between a quiet headline and a coastal disaster can come down to which way a piece of seafloor happened to move, in the dark, in the middle of nowhere. The machines flinched, and then they relaxed, and almost no one will remember that for a few minutes the middle of the Atlantic set off an alarm. But the seam is still there, still tearing, still releasing its strain one swarm at a time. The ocean kept its secret this time. The only honest question left is not whether it will shout again, because it will. The only question is where, and which way the ground will move when it does, and whether, on that night, the 3 levers fall the way they fell on June 17th, or the other way,